All right, well, it's great to be here, always great fun to come here. I think I've been coming here off and on for almost 20 years, maybe 18 or 19 at this point, so always happy to do it. So this is the first of...
Is the mic on?
Yeah.
It's on.
Yeah, it's on.
It says it's on, it's just probably not aimed at my mouth. There may be nothing we can do about that. How's that? A little better? Yeah, okay. So this is the first of 3 talks that are going to talk a little bit about attosecond stuff and dynamics in atoms and molecules that are strongly driven, and using molecules and nanospheres and tricky things to try and control light. So it's all about light. And I'll start out talking about attosecond light. And the sort of application that I would hang this on, just so we can think about something, is this idea of trying to do what I would call fundamental chemistry, trying out that phrase. So the idea of chemistry as it really, really gets going, not chemistry as in where does it end up. So we'll see if we like that. So I take the title of the thing seriously, and I'll try and talk about what are the challenges for the future of this. How this will go. I realize that it only works when I look to the left. Oh well. Okay. So what I want to talk about really is the Nobel Prize that was awarded for attosecond physics. 2 of these people are close collaborators of mine that I have, I don't know, about 50 papers with, and met when I was a postdoc 30 some odd years ago. So that's my postdoc career advice, is make good friends. Go back, get in a time machine, go make good friends. I won't talk about that. I will mention my one Nobel connection, which is that I live in Louisiana. I live on the Mississippi River. And actually, the first big thing that Nobel's invention, which was stabilized nitroglycerin, which we call dynamite, was to clear the Mississippi River, which was blocked and not open to year-round navigation. It was blocked by accumulations of huge amounts of wood and stuff that had fallen into it. Some of these rafts were several miles big, and they still have some of the wood, and they tested and started being added to the rafts 400 and 500 years previously. So I mean, the river was very blocked, and then they used dynamite to open it, and that's sort of how you think of the Mississippi River up to today. So anyway, I want to talk about timescales in chemistry and physics, and I'll just go through this quickly because you know this, that chemical reactions are kind of done after microseconds. You can probe how the chemical reactions happen, how you go from some initial set of coordinates and reactants over or through or under some barrier to the land where you say the chemical reaction is done. And so then you can probe that at various levels. You can look at fluorescence, which is sort of nanoseconds. You can look at transition states using something that has picosecond or better resolution. You can look at molecular vibrations once you have femtosecond resolution, or you have spectroscopy that can look at the vibrations. And as you get down to the femtosecond level, you can start to look at valence electron dynamics. As you go below a femtosecond, you can start to look at core electron dynamics. And the shortest laser pulses that we make at the moment, that people make, are sort of, call it 60 attoseconds. But it's not too hard to make 200 attosecond pulses now. And if you think about the time scale for just a Bohr electron to go around, that's about 150 attoseconds. So the attosecond is sort of the base time level for if you want to think about electrons. And of course, electrons are the lightest things in regular matter. And so that is sort of the fundamental time scale. So that's what we try and think about. And so some fundamental questions. This is just a not ordered, not very good list, but basically the idea of what we're trying to deal with when we do AMO theory in attosecond physics is the fact that light fields give their energy to electrons. So it's electrons that get the energy, And one question you'd like to answer is, how does this energy transfer from the light to the electrons happen when you have a complex system, by which I mean a biologically interesting molecule, for instance, okay? And of course, once the electrons get the energy, they move and the energy is given to the nuclei. And again, how does this happen exactly, okay? Our standard picture of how that happens is it happens sort of adiabatically, slowly over time and in a way that sort of keeps the system with as little excitation as it can have, and just enough to get over a reaction barrier or whatever like that. So if things happen slowly and adiabatically, we kind of understand how to do that, but things don't always happen slowly and adiabatically. And so the energy is given to the nuclei, and the question is, how does this happen? And downstream of these attosecond or femtosecond timescales, right? Attosecond to get the energy from the light field, femtoseconds to pass it on to the nuclei. What's the dependence of these things downstream? And for that, I always have my movie analogy, right? Which is, you got a picture, you're watching the movie at home, and you miss the first 10 minutes of it. And the question is, does it matter? And the answer is, not always, right? Maybe you're watching a standard rom-com, right? If you are watching When Harry Met Sally, if you came in 10 minutes late, you'll be fine. You'll figure out, oh yeah, they're friends, they're going to end up together, right? Not yet, but they will, right? You miss the first 10 minutes of a Hitchcock movie, you are screwed, right? I mean, the first 10 minutes, try leaving out the first 10 minutes of North by Northwest. Nothing. I mean, you will know nothing, right? Actually, missing the first 30 seconds of North by Northwest will leave you pretty much behind the curve for the whole movie. So the question is, are there interesting movies and outcomes that really depend in some way on what happens at these very fast timescales? Or are there cases where that just sort of gets averaged over and it didn't really matter how the energy was? So then the real question for us at this conference is, can AMO theory address the bottlenecks that we face to predict and explain ultra-fast experiments that people are doing now and are going to do a lot more in the near future? And the bottlenecks are the ones that you know about, the standard bottlenecks of scaling and quantum mechanics. The other bottleneck that you'll hear about, and I think that Luca will also talk about, is just sort of having the coordination and the number of people to, on the theory side, to match the scale of investment and people on the experimental side of the equation. And so I would say, are there one way you could phrase this is, are there fundamental chemical processes with attosecond timescales that we don't currently understand? Okay, my answer to that is I do not know, right? But that's kind of what I mean about fundamental chemistry, right? And I would just point out, like as a historical point, is because I've been around long enough, and the state of the art was picosecond high intensity lasers when I started, is that at every phase, as we've gone from picoseconds to 100 femtoseconds to few femtoseconds to attoseconds, there's been a significant number of people sitting around saying, there's nothing interesting at that smaller time scale. We have all the tools we need. We understand everything that's going on. And my response to that has always been that, since the Egyptians started predicting the time scale of the Nile going up and down, there's always been new and interesting. That was the 1 year time scale, right? There's always been new and interesting things at every new time scale, and so you wouldn't want to bet against this. The other thing that I want to say, this really you could just leave after this slide and have gotten most everything out of my talk, is that the near future is that we're generating lots and lots of attosecond timescale experimental data, because the LCLS, the X-ray laser at Stanford, has been upgraded to run at much higher rep rates and much higher duty cycles than previously, by factors of 1,000. And that people's attosecond experiments in laboratories, which up till now have been run at kilohertz repetition rates, so the laser firing every 1,000 times a second, are upgrading to megahertz. So another factor of 1,000. So at the large facilities, a factor of 100 to 1,000. In people's laboratories, factors of 1,000. So just much, much more detailed data than we have currently. And that's a real challenge to the AMO theory side, I would say. So just people have all sorts of sources. There's an Attosecond, there's the Fermi facility in northern Italy produces XUV, intense XUV pulses that have attosecond time structures to them. At the LCLS, the X-ray laser in California, they have demonstrated and have attosecond pump, attosecond probe X-ray experiments. So this is an experiment where they make 2 attosecond pulses. They're both about 200 to 300 attoseconds long, and they can separate them, and the 2 pulses have different frequencies. One is twice the frequency of the other. So they know which one did what, because they're separated like that. So this happened, and they had a very interesting result from looking at transient absorption in water. And then in the laboratory, people in Berlin, Mark Fracking and Bernd Schutte, have demonstrated doing attosecond pump, attosecond probe experiments in a laboratory environment, something that doesn't cost $1 billion to build, but costs a few $1 million to build. So these are all things that are on the horizon or happening now. So I want to talk about one of these sort of fast attosecond processes that we sort of understand but don't understand as well as we should, and that's attosecond charge migration, and I'll tell you what that is. But LSU is in a attosecond charge migration collaboration funded by the Department of Energy with PIs. Lou DeMoro is at Ohio State, Bob Jones is at the University of Virginia, Meta Garda, Ken Lapata, Francois Mauger, and myself are at LSU. There's about 15 people involved in this at any given time on the payroll. This is just some of them. And so here's sort of, if I push the button and the movie goes, which you never know, good. Here's charge migration. So the idea of charge migration is I have a molecule, I have something like, this is bromolanilene, I think. So this is a bromine atom, this is a benzene ring, and this is something over here. I forget, actually. I think, yeah, exactly. Thank you. And the point is that we made a hole on the bromine. The bromine has lots of electrons, and it's perfectly willing to give one up if you shine light on it, like a strong field. And so that creates a hole, and you can make it as fast as you want. You can make it in a few hundred attoseconds or 50 attoseconds, or you can make it how we did here, which is by fiat. We said, we think the hole would look like this, and we did some constrained minimization procedure on that so that we didn't create too much excitation out of localizing the hole. And then what you see as the movie runs, well, maybe I have to make the movie run again, is you see that the hole that started out on the bromine migrates over to the other end and then back again. And it does this back and forth because the hole that you made is an excited state in the cation, right? That's one way to think of it, right? So I made a wave packet, and the wave packet is moving back and forth. And the interesting thing is it does this in about 1.7 femtoseconds. So it's less than a femtosecond to go across and to come back. And that's much faster than the atoms can move, because the atoms are big and heavy. Maybe not the hydrogens over here. They're light, and they maybe could move in a few femtoseconds. But this is a thing that we think happens. Okay, so attosecond charge migration is not the same as charge transfer, which is another thing people talk about. So just say briefly what it is. It's really this, what you saw in the movie, this coherent particle-like motion of an electron density hole. Yes?
Is this time scale typical, or is this very special to this molecule?
Very typical because of the broadband nature of the excitation process. So you just look at the scale of states that you can populate and how far apart are they in energy. So The actual more interesting part of this that we don't understand very well is why the whole like moves so nicely and coherently, okay? But it does, and we know it has to do with the long-range forces as much as, you know, the short-range correlations, but it's definitely, so that's what we're looking at. We know we can trigger it by pump excitation, or we can create a molecular ion in a non-stationary state. We see in many, many systems, but I'm going to show you in not every system, which is important, right? Once you start seeing it, you know, in your simulations showing up a lot of places, it becomes really important to find a case that, you know, right, cases that it doesn't work for. We definitely have those. It's a long-range coherent process, you know, and it is, we think, part of the initial process of photochemistry, right? Again, it's sort of the movie question, right? This is for sure the first 10 minutes of the movie in some sense, when the excitation is fast, but does it matter is a different question. Yes?
How many electrons do you include in the simulation?
This is done, I'll tell you how this is done. It's TDDFT, and there's probably 18 electrons, something like that. There are frozen cores, but there are lots of active electrons.
Sorry, quick question.
Yeah,
If you were to do
absolutely.
simple tight binding of a single pole, how bad would it be? Is tight binding on a tiny lattice?
It's done on a, again, on a next slide, it's done on a quantum chemistry program called NWChem, which is, if you're familiar with Gaussian, it's like that.
No, I meant more like if you were to just do simple kind of tight binding on a
Oh,
lattice,
sure. Yeah.
just
You could,
disregarding the
you may
lattice.
sometimes, right? It depends. You know, again, you can set up tight binding situations where it does and doesn't happen. So I'll tell you the conditions for when we think this happens. Well, or I'll just give it away. When you have these pi-bonded orbitals that sit above and below a relatively planar molecule like this, they provide basically a little highway that you can hop your way across, and you can hop your way back. But again, it's all the electrons working together, so it's a kind of an interesting process. Yes?
So in a tight binding model, would one have to fine-tune all of the tight binding couplings to reproduce the TDD?
I don't know because I don't do that. But it's more the so if you do it in a tight binding thing and you limit it to 2 states, and one of the states is over here and one of the states is localized over there, it will work, right? It's the question about all the stuff in between, right? How does it get through? How does it get off the bromine, through this bond, into the ring, into that bond, onto the nitrogen or whatever, carbon or oxygen or whatever we put there. You can put what you want there. It's nitrogen in this case, but you can do other things. You can hang other things there, as I'll show you. And so what are the conditions when it can do that? So we'll get there. Right, and this, I missed, maybe I said 1.7 femtoseconds. It's about 700 attoseconds to go across and 700 back. So 1.4 attoseconds, depending on exactly what you hang here and what the nature of the bonding is. But you can see that this is a conjugated system, right? So that's kind of one clue that we've found. So this, you know, the alternating double bonds, and that will give you the pi-bonded orbitals above and below the plane that act as your little highway that you can hop along. If you want to think of it, it's better to think of it as hopping, I would say. So it's not charge transfer. I mean, charge transfer is on a longer time scale, and that's really when charge started out on one side of the molecule and gets trapped somewhere else in the system. And that can't happen purely electronically because you can't get rid of the energy. But when the nuclei start to move, they can rearrange and configure themselves in such a way as to trap in a way that is irreversible the charge somewhere else. Charge migration is just what we've been looking at. It's this on a less than 10 femtosecond time scale, long-range coherent process. And again, it's the initial step that has to hand its energy off, or at least part of its energy, off to the nuclei. And I want to say that the idea of charge migration is not dreamed up by theorists out of nowhere. It's actually invented by experimentalists working with theorists in the mid-90s, trying to explain a seminal set of experiments that I'm not going to go through. But basically, they have a long polymer chain that they could hang something off of that they could resonantly excite. And then they could look at what bond would break when they resonantly excited this color center over here. And they found that instead of sort of every bond breaking, they could selectively, by putting energy in here, they could selectively break a bond over here. And they invented this idea of what they called charge-directed reactivity, which is just basically the idea that you're making a hole and that hole propagates. And if you have a weak bond somewhere and that hole gets there, then stuff happens and the bond can break. So it didn't come out of nowhere. And there have been experiments over the last 10 years to really start to investigate this. And, some of it also goes back to papers from the early 2000s, some coming out of Lawrence Sederbaum's group and some coming out of Rafi Levine's group, where again, they just sort of showed that if you suddenly make a hole in a molecule, that can be an excited state in the cation, and sometimes that leads to coherent motion back and forth across the molecule. And they showed that this would happen, even in pretty big molecules in sort of less than 10 femtoseconds. So faster than you could expect most nuclei to move, unless they were hydrogen-like. So this was an idea that again, gained a lot of currency in the early 2000s, and then there's been experiments the last 10 years or so. And so we got interested in the idea that, just what we've been discussing here, which is there such a thing as attochemistry? In other words, following this rapid ionization or excitation, how does that lead to the downstream processes? And also, when we started this about 10 years ago, there were a lot of questions from the experimentalists. How should we initiate charge migration? Are there ways to control it? Are there rules you could learn about when it happens and how fast it happens, how generic and systematic it is, and how does it couple to nuclear dynamics, and how does this initial coherent hole, if you make it, get dephased? I don't have a lot of great answers to that last question, but this is about the future of AMO theory, and I would just say that's part of the theory. How we got started in this business, because you have to pick some way to get started, is to go ahead and do calculations using time-dependent density functional theory. And because it's general, the scaling of solving the TDSC for so many electrons is really, really hard. So you do time-dependent density functional. One thing about all sort of dynamics problems is you have to think carefully about your initial state. We've thought carefully about how to make the initial hole in the system when we were not simulating the process of making it, but actually just sort of trying to guess what a reasonable hole would be in a given system. So for the initial state, we wanted to emulate what would happen in a strong laser field to build a hole on some halogen that we had hanging on one end. This is bromobutadiene, so bromine atom again here, bunch of carbons again with alternating bonds, some hydrogen terminating it. So we wanted to simulate making a hole over here. So we do that using energy minimization techniques. So we have multiple regions of the molecule, and we make sure that we don't introduce a whole bunch of energy just by fiat into the system. And so that we're not sort of like forcing the behavior that we see. And then, you can start out doing the local density approximation, or you can do generalized gradient approximations. We've actually taken a hybrid approach, which is, I think I have it on the next slide. We'll skip that one. where basically we mix and match. Yes, sir.
And this chain molecule that you
Yep.
showed,
Yep.
are the carbons equally spaced, or is there a Peierls distortion?
There's a distortion, yeah, that's why the bonds alternate.
And so I might expect some edge states that are localized and not get the charge migration. Just thinking like polyacetylene or something like this.
Yeah, let's talk about that
Sure,
after.
yeah, fine.
Yeah. All I was going to say was a very technical thing, which is that when you do density functional calculations, you always have to pick how to think about the potentials. The local density approximation is actually really good if you're if you have electrons that are close to each other, and it's kind of crap if they're far apart, right? Because it should fall off like 1 over r. So what we actually do is these tuned range separated hybrid potentials that go from being local density like close in to being basically Hartree-Fock at long range. And and it has a parameter that you have to tune, which is, how fast does it switch as a function of distance from being like one to the other. But it turns, and you could just pick that parameter, but it turns out there's a way to pick it that's physically motivated, which is if you look at the energy, so if by self-consistent field, you calculate the energy in the molecule as a function of removing electrons from it. So you go from having, so many electrons to some fraction of electron down to an integer number. Now you go below that. Anyway, this should be a straight line, right? A straight line with a discontinuity, because the slope of this line is your ionization potential. And so you can tune the potential by saying that the slope of this straight line that I get, first, it ought to be straight, and second, that it ought to match it should enforce Koopman's theorem, is a fancy way of saying it. But it should give you an ionization potential that's reasonable. And so we do that, and it provides tuning to the potential, and then it's a lot better than if you just had to guess. Okay. Another thing you want to do, yes?
What is the meaning of fractional number of electrons in the plot?
You can simply, you start out with whatever number of electrons, 16 electrons that are active. You can say, nah, I'm going to give you 15 and a half, and do the self-consistent field and find the ground state of that thing, and that will give you an energy. Just, I mean, it's kind of a problem conceptually, I agree, right? But this, at least, when you do this range tuning thing, you get something because you get this straight line. So I should say, if you use a normal sort of high grade potential from density functional type thing, like PB0 is one, you get a line that's kind of straight, but it's kind of curvy. And actually the curviness is bad. In other words, it's like the second derivative that's a problem. And so when you do the range tuning, you really can get to the triangles here, which is a straight line that has, and so, yes.
Can I interpret that as saying that, like, when I have a fractional number of electrons, you're actually preparing a mixed state of, like, the molecule with a hole in the molecule as you want?
You are certainly, yeah, or you can think of it as we're getting some representation of the Dyson orbital that you would, right? I mean, you can define fractional and electron states. It's not a problem, right? You can build it out of the n=1 and the n=, right? You can, in other words, what you said is for sure you can do that, right? I guess you said the magic words at the beginning. Can you think of it as? And my answer is definitely yes. That's what we do. It's still within a single configuration, but I mean it's definitely like that. So the potentials we use that are LDA-like at close range and 1 over r at long range, they get tuned by this. We don't pick that tuning parameter ourselves. So theory crowd for sure. I've got to say, I usually get through that slide pretty quickly. I find it fascinating, but usually the crowd does not. So good for you guys. The next thing you want to do is you also want to compare this, like you're doing TDDFT, you want to compare it to something that has more correlation in it, right? And so when people do, so like Lenz Sederbaum's group, they do, high-level two-particle, two-hole correlated wave functions. They can't make very many of them, so they'll make 4 or 5 of them and sort of propagate the problem in that basis, right? And so for something that we could compare, like nitrosobenzene, where there's sort of an electron lone pair on the nitrogen atom that you can go and pick an electron out of, because it's a state that sits below the valence level but above the core, so it's like there to be picked off. And if you pick it off, then that hole that you make in that inner valence level does not go anywhere, okay? But it creates a disturbance in the valence electron density that does propagate out and back. So see, you don't have to make the hole directly in the density that you want to move. You just make a localized disturbance, and that also works. But anyway, this is a long wind-up to say that in this case, for making a well-defined initial condition hole that we could agree on, because the inner valence orbital is the same in DFT or in some higher level quantum chemistry. It's not hard to get the inner valence levels right. So we agree on the initial state, and then it turns out we also agree on the dynamics. So that's useful to know. And it's in, yes, sir.
Homo minus 1, homo minus 2, I mean, does that labeling is not exactly the same?
The labeling is,
Right, so
the labeling, so our labeling, I do want to say this correctly. So there's 2 things you need to do to get good agreement between this. First off, they just do what they do. And they have labeled these because these are the 4 orbitals they have. Done, right? So they get to label them, right? We have a bunch of orbitals, okay? And by doing the tuned range thing, we get them to be in the right order, right? I mean, it doesn't have this sort of shuffling problem that Hartree-Fock theory has, where things end up in the wrong place. So you have to get them all in the right place. You have to use a potential that gets them all in the right place. But then we look at all our 18 orbitals or however many we have, and we say, looks like all the action's only in 4 of them. So we have shown you those 4, okay? Whereas in the ADC calculation, these are the 4 they have, okay? And so I would claim that's pretty good, right? That the four that we find that where things are really happening, right? And we do this just by projecting onto these orbitals as we go along. The behavior matches very well with what they say. So it is what it is. So the challenges for this, for any of these people, and I think I don't know how long I have to talk. I don't want to. Do you know it all? Yeah, okay, fine. The challenges really are, which molecules support attosecond dynamics, how to look at all these things, how to observe the attosecond processes. I think we have a good shot at the time scales and sort of how to interpret these things. So let me just show you a little bit of the kind of metrics that we found. So we make a lot of plots like this, where we have a molecule. So here's the bromine, and you can see here that the distances vary, so that we have this conjugated structure. And then we make a hole on the bromine. So that's the red, dark red here. We make a hole on the bromine at a time. And you can see as time goes on, you can see it delocalize and then relocalize on the other side and come back here and go back there and come back here. And so if you look at the whole number on, for instance, this end on the terminal bond of the molecule, it goes up and down with what we call the charge migration frequency. Now, this is not a 2-state system, right? This is lots of electrons, right? But doing this kind of coherent motion. You can look at the role of bonding. So you can change, for instance, by hanging different things. So even though you've got bromine, you can change the bonding of the chain that it's attached to. So Here's the one we just looked at, bromobutadiene. You can change that a little bit to the alkene, so you still have these double bonds, and you still have pretty good charge migration back and forth, but at a different frequency. And you can also, do bromobutane. You can change this to where the chain is singly bonded, and well, you put a hole on the bromine, and it's just happy to stay there. It just hangs out there. It can't really get into the chain, and no charge migration. So this is the sort of base level theory prediction that we were trying to provide. And then we've gone on to think of, well, the things I've been showing you are sort of like donor-acceptor systems, where we have a halogen, we have somewhere where it's easy to make a hole, we have a ring, and then we have something on the other side that may or may not want to accept that hole, right? So you can also turn around and think of this in terms of electron donating and electron accepting sites. And you could have the idea that, that if you had something over here that was a weak electron donor, that it would not be happy to take that hole when it comes to it. Or if you had something that was a strong electron donor, it would donate the electron to the ring and take the hole, and that would be good. So you can try different things like that, and I just want to say it kind of works like you would think. So if you have something that is accepting of the electron, like you hang CF3 off the right end here, then you get very good charge migration. Start here, go over there, come back. But if you hang NH2 over here, you can also get good things. So you can look at how much of the hole that you initially make actually ends up on the other side, and you can calculate a contrast, which is basically just the contrast in that wiggling diagram I showed you. And then you can plot that for hanging many, many different acceptor molecules off that side. And this actually lines up pretty well. The orange triangles are our calculation of this from TDDFT. The blue is actually something called the Hammett factor. Does anybody know what that is? I didn't either, but it's something that chemists use that is basically like how acidic is the thing. So it just sort of shows you how electron accepting or donating the thing is. And it lines up very well. In other words, so the idea, and so this is like primitive attochemistry, right? We can say, well, look, if you hang this on the other end, it's going to want to migrate over there. And if you hang that on the other end, it's not going to want to migrate over there. And so maybe you get two different downstream chemical processes.
I have a question regarding this, sorry, my long-lost chemical intuition. So the next one. So I would seeing the picture on the left, I would say that the second moiety is a donor, but it is a plus, what we used to call plus I, induction donor, so the sigma bond. Whereas an H2 is a plus R donor, because there's a long tail that you can share in couple with the P system. So my intuition would tell me that the plus R donor would be qualitatively different from the induction donor, and this is consistent with you say I need a conjugated system. But there, if you look at OCH3, which is also a plus R donor, it's kind of the same as CH3. So that is where I don't follow anymore. So why isn't there this, and why am I wrong in expecting this gap? And
Yeah,
isn't there?
I don't know. You're asking me a chemistry question. Second only to being asked a math question, right? I mean, but it's the correlation is interesting here, right? I mean, they really do, the Hammett factors really do line up this way, and so I think it's an interesting question too, but it's more of a correlation than a thing. I mean, we know more than I'm saying, but we should discuss it more. So we learned some things about attochemistry, and so that was great. And I just put a very brief plug at the end of it, sort of to, that was sort of thinking about things, where you might make a hole in a femtosecond or so. But, there's also X-ray spectroscopy for probing transient dynamics. This is something that started out in the mid-2000s using strong fields and attosecond pulses, but has now moved on to being something that happens in the X-ray regime at the LCLS. And so I only want to leave you with, this is sort of the problem that we're confronting, or the kind of thing that we're being asked to calculate, which is you have an energy spectrum, you put in some X-ray pulse, and then you at a later time, you probe the system, and you see that its ability to absorb light at different frequencies changes as a function of that delay, right? And this is some massively complicated problem, right? Where you have dumped a bunch of energy into the system in a very short amount of time. You know the electrons took that energy, and you have to work on passing that off to the nuclei. And we have ways to do that if the energy is passed, as I say, sort of adiabatically in the sort of lowest energy minimized kind of way, where the electrons are dragged along with the nuclei as they go. So sort of the Born-Oppenheimer approximation, as often as you can, as long as you can, until you get to like something like a conical intersection. Then you try and follow it through that, then you're back to, right? So we know how to do that sort of thing, but we also know that that's not how life really is. And so as people do more and more of these X-ray experiments where the time difference is measured in, where they measure the spectra in time differences that are less than a femtosecond and out to a few femtoseconds, and things are changing, that's really the challenge that we face. And I think, yeah, I think that I will leave it there. Thanks.
Thanks a lot for the talks. Several questions for the audience.
I guess like, if I understood the point that you ended on, is that like, these dynamics are so fast that you're able to see like the coherent motion of the electron.
Yep.
And if you weigh the factor of 100, now everything should be like the Born-Oppenheimer, where everything is kind of like incoherent. Is the goal of like these studies to kind of understand how kind of like this adiabatic process come in, or is it even like further along, like how does these initial coherent oscillations indicate the chemistry of like photosynthesis?
It would be the second, would be my basic interest. In other words, I'm not really interested in what happens 400 femtoseconds later, unless it's something that is impacted by those short-term dynamics, and I freely admit that not everything will be. But the basic thing is you put a bunch of energy into the system, and actually only a few things happen. And so what determines those few things that happen and the branching ratio between them? And also, if there are things like photovoltaics, right, you'd like to make electron hole pairs that separate and stay separated. And most of the time, right, I mean, the reason that they're not 100% efficient is because they don't separate, they just recombine. So you might also want to, design something that worked better. But that means you need to understand how the electron and the hole interact in the very first few femtoseconds, because that's when they tend to decide that they're not going to separate, and they'll orbit around each other and then recombine. And that's what usually happens, right? So I think it's both of those, like what downstream process and what structures could you build to encourage the behavior that you want downstream.
And maybe asking the opposite question, are there like physical like molecules where it is known that these like coherent motion has a significant impact? Or is it like...
Right, I would say the answer to that is no. Yeah, that's the stage that we're at, right? So the experiments that are done are sort of sandbox demonstration experiments, and so they're just on things that, where they're pretty sure they pretty sure that the hole, they know exactly what hole they're making, and they kind of understand it as almost a two-state system. And so then you make a measurement, and sure enough, it oscillates. And that's the stage that it's at. But I mean, my message is really, we're about to be inundated with 1,000 times as much data, so it won't stay that way. So let me just show you one more thing. This is an example. This is a slide from a paper from Mauro Nazzoli's group and Fernando Martin that appeared in Nature Chemistry last year. And I just want to show you, this is something where they put the energy in 200 attoseconds, and they find that this molecule is much more willing to absorb a second pulse than if they hadn't put the energy in. And this is sort of the curve that they show you. And you don't have to know what this is at all, except to read the scale. It's like 50 femtoseconds. The thing that they're looking at, a certain fragmentation channel, it comes up very quickly in less than 10 femtoseconds, and then it decays off. And the black line, and with the shading outside it, represents really our state-of-the-art, the best that we can do at this sort of putting energy in and handing it off. And they're following hundreds of trajectories. It's very complicated. And you can see that the actual experiment, the dots, you can see they're oscillating. Can't you see that? They really are. And if you Fourier transform that, you get this, which has a huge, peak here. In other words, out here at 20 femtoseconds, it really is going up and down. That's not just your eye telling you that. And my point is that this is at a kilohertz repetition rate of the laser. It's firing 1,000 times a second. When they do 100 times better than this, they're going to fill all those little wiggles in, and we are not, we are not going to follow those wiggles if we don't sort of, continue to make progress. Okay.
Kind of running out of time, but I
Yep,
would just
yeah,
have
yeah.
a very short follow-up question. So I was also
Yeah.
trying to understand
Absolutely.
this dephasing, right? So the generic expectation would be you have a large system
Mm-hmm.
with all these many electrons,
Yep.
a large Hilbert space.
Yep.
Things should dephase, right? Then the question is on what scale? So then, is this generic now what you see, or do you also have molecules where these oscillations just stand out and dephase?
So I think the
the
more,
oscillation
right, so the standard way of thinking about dephasing is just that the nuclear wave packet that you make spreads out,
But even
right?
these many
So the
electrons-
nuclei start to move, and it's not that other electrons get excited, it's that the nuclei start to move,
So you always have a low-dimensional subspace for the electrons.
for instance.
And that's
That could be
generic.
one way to do it, but I want to say that people have studied, for instance, making holes in benzene rings, and Alex Kulev's group, for instance, has found situations where you would calculate the vibrational period for the ring or whatever, and you would say, well, that's the dephasing time, because if on a time scale where the nuclei can move, that's the time scale of the nuclear wave packet spreading, that's your dephasing, you're done. And they find it can last much longer than that. So, these are systems that are coupled. And so there are examples already in the literature, one or two, where this coupling out and back coupling between it can keep this coherent motion going longer than what you would guess from the vibrational period. So that's a very interesting result that, I don't understand it better than what I just said, but it's a very intriguing result.
Okay, so thanks a lot.